This is the Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known.
Well, welcome to the Math Map Book Club, where Kirsty Gilpin and I and our team of friends who just love math or have big questions in math join us each week. Wednesdays at 1 p.m. if you'd like to join us next week. Today is July 22nd, where we talk about the Math Map curriculum used by Classical Conversations communities. And this is the last, I believe, of our summer series. So, Kirsty, what are we going to talk about today?
We are going to wrap up today by talking about multiplying and dividing fractions. And I said last week that I think adding and subtracting fractions may be the most involved. I don't want to say hardest, but maybe the most involved, because we have to really attend to whether or not we have common units in our fractions. So this week, we don't necessarily have to worry about that, but we're still going to talk about what it means to have units as we look at this. So let's dive in. And the first thing I want us to remember is that when we talk about units, there's a hidden multiplication. And so I would start with your students and have them read aloud, identify the units. We've done that before, but this time identify the scalar also, and then write out what the multiplication is. And I think that that will just help us to remember. So let's very quickly do this together. If we read our first line there, does somebody want to read that for us? Tell us what the units are and the scalar is.
Five Smarties,
Mm-hmm.
and the units will be Smarties. This scalar is 5.
Mm-hmm. Yep.
Okay, and I don't know how to write out the multiplication of that. So 5 times 1, because then the multiplication will be 1.
No, it's
Okay.
really just 5 times our unit. So
okay.
we have 5 times Smarties. Yep. So how about 5 centimeters?
So 5 centimeters, the units is centimeters, the scalar is 5, and it would be 5 times cm or 1 cm.
Yeah. I'm going to come over here because I'm going to take this off. It would just be 5 times 1 Smartie, right? 5 times 1 centimeter. How about the next one?
5 times pounds or libs, so 1 pound.
1 pound, good. All right, the next one's the hard one. What's the unit?
5 times 1.
Yep. Now, I could make an argument that I have 1 5, but usually if I have 1 5, I'll write it differently. And so I would say here, this is 5 1, so I have 5 times 1. And then how about our last one?
5 times 1 6.
Yep.
Yeah,
5
1 6 is the unit.
Remember, we want to, so we sort of started skipping steps toward the end. So with our students, when we're unfamiliar, we want to always start by reading, right?
Yeah.
So 5 centimeters, centimeters are my units, 5 is my scalar, so 5 times centimeter, right? 5 pounds, pound is my unit, I have 5, that's my scalar, so then I can write it as 5 times pound. So a lot of us want to jump right to the end, right? 5, 1 is my unit, 5 is my scalar, so 5 times 1. And then really with our fractions, for our students that are gaining familiarity, we really want to emphasize reading that first, because when we read it, we hear 5 6. And now I can say, well, 6 is my unit. And so it would be 5 times 1 6. So remember, we're trying to help our students to become familiar with fractions through language. And the best way we can do that is being consistent with everything, with all of our units, helping them to see that it's just one more type of unit when we're talking about it in this manner. So let's just review. We've reviewed this several times, that for multiplication, we can use our commutative and associative laws to see that we can move our, when I say move, right, we are rearranging and regrouping. So if I said I have 5 times 5 Smarties, right, the associative law is what lets me say that that's 5 times 5 and multiply that first, Smarties. That's what lets the associative law that takes those 5s and groups those so that I can say that that's 25 Smarties. If I was looking at 5 centimeters times 5 centimeters, I'm going to use both my commutative and associative laws because now I want to rearrange it so that my numbers are next to each other. And then I'm going to use my associative law so that I'm multiplying my 5s and my centimeters. When we think of the commutative and associative laws, do they hold for division? No, right? If I said 5 divided by 6, that is not the same thing as 6 divided by 5, right? 4 divided by 2 divided by 3 is not the same as 4 divided by 2 divided by 3, or 4 divided by 2 divided by 3, right? When we group differently with division, we get different results, and we're going to see that. However, we can rewrite division as multiplication by the reciprocal, right? That is our multiplicative identity law, right? So that division and multiplication by the reciprocal, right? It's not quite it's more the reciprocal law, that those are equivalent. And so I can take my 5 Smarties divided by 6 and rewrite that as 5 Smarties times 1/6. And then I can use the commutative law and the associative law to take my 5 times 1/6 and get that I have 5 6 Smarties. Although practically speaking, if we're going to share Smarties, you can just give me a whole Smartie and not worry about the 1/6 part.
That would be weird. How do you get
Wouldn't that be
one
hard?
sixth of it? Well, you know those
Yeah.
pill crushers? I guess you'd have to use a pill crusher to like cut it in. I don't even, can you do 6 of a Smartie though? That would be so tiny.
It would be pretty hard.
A whole a package of Smarties. So 5, 6 of a packet. But then if it's a whole, you get a whole sleeve of.
There you go. That might be easier. So, or maybe we'll have Kristen like use her mortar and pestle and crush up the Smartie and then weigh out 5 6. So, or if you're over here in the UK, Smarties are like way better M&Ms. And then I'll just take all of them and not share. Oh, that was bad. I shouldn't have said that out loud. All right. So we want to remember, again, as parents, we want to know why these things work, because we want to appropriately ask our students, right, to name what lets them do these things, right? Now, that might mean with our little ones that we just name it for them so that they hear it. With our older ones, we might ask them why. So it doesn't mean that you have to always start off and always say, look at why and show all the steps. But I really think it's important for us as parents to understand these laws and the power of these laws, because our children from a young age are memorizing them and they have no idea why. So as parents, I want you to see that these are really central, fundamental, elementary, right? When we think about that idea as the elements of mathematics, elementary to mathematics, and why we can do the things that we do. Because if we don't take it for granted, then we're going to be better able to help our students to see how these pieces fit together. So let's think for a minute about circumstance. And I use that because in the math map, we've talked before that we always say scalar times vector, usually. And this time I've written scalar times unit. And so what matters is the order. Because of the commutative law, we know that the result is the same, right? The commutative law says that the result is the same. But I want us to just be thinking for a minute that if I'm talking about, if I have two numbers, I have a 2 and a 3, I can think about that in terms of 2 being my scalar and 3 being my unit. Right? Do we ever do that? When would 3 be our unit? What's something that all of your kids have learned how to do if you've been in CC Foundations at least 1 year?
Count by threes.
Count by threes.
I shouldn't
Right?
tell you this, but like when I had to do a new password, I would do that. And my latest password is 369 1215 1821. That big
Now you
long
can go
string of
change
numbers.
it.
Yes, now I have to go change it.
Maybe it's count by 4. So I'm just going to go through the whole skip count and just hack it.
Yeah, you can't start the song and then stop after that.
So we see that we can use 3 as our unit, right? And if I have 2 3s, we usually just go, oh, that's 6. And then we might think 6 1s. But we could also say it's 1 6. We could say it's the same as having 3 2s, right? 12, if I had 3 12s or 3 dozens, when do we use dozens or 12s?
Eggs.
Eggs,
Cupcakes.
cupcakes.
Donuts.
Yes. All right, my pickleball team's name is Dinkin' Donuts. So, yes, donuts. Right. All the good baked goods, right? All the really yummy stuff seems to come in a dozen, right? So we have our dozen is a very useful unit, which is 12s. And I've given you just some different ways we could write this in terms of a unit of 36 or a unit of 1, units of 9, units of 4. What other units could I use to describe 3 times 12? What if I was counting by 6s? How many 6s would I need?
2.
Yeah, you could ask the question better. We don't know what you're asking.
So 3 times 12, right? We've got some examples here. I could say it's 136, or I could say it's 36 1s, 4 9s, or 9 4s. What are some other ways I could express it? What other types of units could I use other than 12, 36, 1, 9, and 4?
Oh, like 6
So
times 6?
6 sixes.
6 6s.
3 12s,
3 12s,
12 3s.
12 3s. I think there's 2 more.
It did 2.
2 18s.
13.
18 2s. Could there really be an infinite number? How many halves would it be?
Yeah, we're just giving you whole numbers.
Mm-hmm.
It could be -6, -6.
Yeah, that's hard to have it, right? That would be a hard thing to have negatives, but we could.
Mm-hmm.
If you owed me donuts, you could all have -12. I like this idea.
You just want to
All
take
right.
all of our snacks today. Like, what is going on?
I know, it's terrible. All right, how about our last one? What about 16 5s? How else could I write that?
8 10s.
8 10s,
80 and 1.
81s.
40
So
and
notice
2.
40, yeah. So there's so many ways. Think about doing this with your students. It's the same as what we were doing with factoring, but now we're just thinking, right? That's why I called this circumstance, because we're just thinking about our numbers a little bit differently, because now we're saying I'm scaling and I have a unit. And usually we're going to think of that second number as our unit. What am I counting by? So now let's look at scaling fractional units. Again, let's read it aloud. If I said, what's half of 8? What would that be?
4.
4. There's my 4. What if I said half of a half?
One
Quarter.
A quarter. What if I said a half of a third?
1/6.
1/6. So here, what was my unit? Half of an 8. Which was my unit?
8.
8. And I scaled it by 1/2. Right. Can I scale things by a half? Yep. So if I have a half of a half, what's my unit?
1/2.
1/2. So if I scale that unit by 1/2, what's my new unit going to be?
1/4.
1/4. If I started with a third and I scale that by a half, what's my new unit going to be?
1/6.
1/6. So again, I've written it on the right-hand side so we can see it with language, right? A half of 1/8 would be 4. A half of 1/2 would be 1/4. A half of 1/3 would be 1/6. When we hear it, a lot of us can do that more readily than we jump straight into multiplying the fractions. So start with your students by reading it out aloud. So that
I like that of, like using the word of instead of times.
Yes. So I'm over in the UK, and when they do their multiplication tables, they usually don't say times. So instead of saying 4 times 3, they'll say 4 3s. And you really quickly get to hear the scalar and the unit. Right? 4 3s are 12, 4 4s are 16, 4 5s are 20. And it makes sense in a way that sometimes saying 4 times 4 interrupts you a little bit. So I don't know if that would be allowed for Memory Master in the US, but I think it's a lot smoother way, and it linguistically, I think, helps our students to connect the idea of what we're doing when we multiply, that we're scaling this unit, right? And that we can see when we skip counted, that I was skip counting 3s, that was my unit, that's what I was counting by. And so if I say I have 4 3s, I'm now scaling that unit to get to 12. So again, just thinking of that. And then when we use fractions, we insert that half of, or a third of, or a quarter of. And when we do that, all of a sudden our brain, to me anyway, right? This is my brain, may not be yours, but my brain immediately, if I said a quarter of a 6, I see a picture in my brain of a circle in 6, and then those 6 being cut in quarters. And so I immediately have sort of a visual picture in my brain, not necessarily that it's a 24th, but I know it's small. I have an instinctive idea that it's got to be a much smaller fraction.
That is so helpful, because I feel like I've always struggled with multiplication is supposed to give you a bigger number. But when your scalar is less than 1, if you're thinking of it that way, that makes so much more sense to think of, okay, we're scaling it by this, but we're just taking a part of that whole instead of, yeah, that's really helpful to me. Thank you.
And you're right. If we think of even if I said, what's 4 of 1/3, my scalar is greater than 1. Do I expect a number bigger or smaller than 1/3?
If you said if the scalar is 1/4,
if the scalar was 4, if I said 4 of a third or 4 thirds,
okay,
all right, I would expect it to be bigger than 1/3, and it would be 4 thirds or 1 1/3. All right, if I have a half of a third, I expect it to be smaller. So yes, when I start looking at that as a scalar and a unit, now my brain starts to almost instinctively start to see. Now, my brain may do it instinctively because I've done it for a long time, but the more that your student sees images, right, so looking at the flashcards, for example, those fraction flashcards have images of all of the fractions. So that's going to help them to have that mental picture of what does a 6 look like. And then if I only want half of that, we immediately go, oh, it's got to be smaller. And we also start to see, just like you said, Jana, that my scalar less than 1, I'm going to get something smaller. It starts to click and make a little bit of sense to us because it's following the same rules that we've been looking at for everything else.
And I don't know if you're going to get to dividing by fractions, but that's another one, just kind of blows my mind. But since it's the reciprocal, right, and they're reciprocal operations, then if you divide by something smaller than 1, it's going to get larger. And if you, anyway, that one's still a little hard for me to visualize, but
we are going to get there. Okay. And it may not help you, but we are going to talk about it. All right, so let's think about why we multiply across, right? That's probably the rule that we all learned, is why we multiply across, meaning we multiply our numerators together and then we multiply our denominators together. So if we look at 5/2 times 4/3, right? And I rewrite that out as 5 times 1/2 and 4 times 1/3, I now see my fractional units. Now, the next step that I'm going to do, the next step here, after I've shown my hidden multiplication, is to use which law lets me reorder?
Associative?
No. Commutative.
The commutative law lets me reorder. So that's what let me do 5 times 4 times 1/2 times 1/3. And then which law says I can group differently?
Associative.
Associative. So instead of 5 times 1/2, I'm going to do 5 times 4, and then I'm going to do 1/2 times 1/3. Right? So notice 5 times 4, those are my numerators. They become 20. Now I have to deal with my 1/2 of 1/3, right? 1/2 of 1/3, right? That's where it becomes 1/6. And so now when I put that back together, I get 26, which is 5 times 4 over 2 times 3. So that's why it works mathematically, because I can pull things apart to multiply them this way in order to see, right, my new unit. So I have my 5 times 4, and then I get my new unit here because I'm changing my unit of 1/3 because I only want half of it. And so my new unit is going to be the 6.
Mm-hmm. Can you also describe, just pretend that I'm my child and say, well, we can multiply across, but we cannot plus across. Can you explain that and put it in words? Because this is really helpful.
Yeah, so here, right, if just don't even look at the screen, right? I would say to you as a child, I'd say, close your eyes and listen to what I say. And I would start with, I have 5 pens and 4 cups. Can I add those to get 9 of something? No, they're pens and cups. So I still have 5 pens and 4 cups. So what if I have 5 halves and 4/3? Can I add those together and get 9 of something? No, because halves and thirds aren't the same, are they?
Mm-hmm.
And if they said, well, they seem like they might be the same, I would say, okay, well, do you want half a piece of cake or do you want a third of a piece of cake? Right? Or whatever it is that they like, right? And pretty soon they're going to go, no, a half and a third are not the same. Right? I want the half a piece of cake. It's bigger. Well, you just said I could add them. So they're not the same. If they're not the same, I can't just add them, right? We have to be able to convert them to a common unit before we add them. We don't have to do that with multiplication because I don't really have to worry about these units, because what I'm doing here is I'm using my 1/3 as a unit. And then when I take half of it, I'm actually recharacterizing this as a new unit, which is 1/6.
You're scaling it.
I'm scaling my unit.
That's helpful to me. You're scaling the unit up or down, but you're scaling it.
Yes.
When you multiply.
That's exactly it. I'm scaling that unit. So I'm not adding, I'm not trying to combine unlike things. I'm actually scaling that unit.
Thank you. This is helpful.
So on the bottom, right, what do we do if we're doing this with students? Practically speaking, do we write out all of the steps that are on the top? No. Practically speaking, we just say, I can take my numerators and multiply them, and I can take my denominators and multiply them. And it doesn't matter if I have 2 fractions or if I have 3 fractions, right? So how would this bottom one simplify? How would I write that if I was a student?
105 over some big number.
So
143 twice is 286.
There you go. Oh,
So-
okay.
So
And
let me
level.
just encourage you that if you are working with your student, start here.
Okay.
Just like there are exercises in the math map where they're not expected to do the calculation, they just have to write it out. Why is that? If we jump to the calculation, do we know whether they were doing it correctly or if they just guessed well? So when they're just starting, tell them it's okay to stop here. Because if they can go from the left to the right, you immediately know that they knew what they were doing, right? Because they went through and did that.
You know that they read it properly and I've seen that
Yes.
form. They still may not know what they're doing.
Well, that may be true, but they were able to follow the process.
Yeah.
Then we can multiply. Now, with your older students, when you're doing this, I would encourage you, if you have students who think, I already know how to multiply, is challenge them to look at this and not just work left to right, but to instead look and go, what is the most efficient way to multiply? So is it more efficient to say 11 times 13 times 2 or 13 times 2 times 11? Is there a different way? Because sometimes one way is easier than another. So I would say in this case, I probably would go left to right because 3 times 7 is 21 and 21 times 5 is fairly straightforward. And every time I move my hand off of the drawing pad, I lose where I am. So that's 105. And then 11 times 13, if you know the trick for the 11s of it's the outside numbers plus the sum for the inside, it would be 143. And then doubling that gives me 286.
Or if you know that 11 trick, you just do the 13 times 2 first, and then you use the 11 trick.
There you go. Either way. So, but I think that's a great conversation to have with students who think that they are ready to jump straight to the answer, is to have them really think through, is there a more efficient way for me to multiply? Because sometimes it makes a difference, not always, but I think it's a good way to challenge your students to be thinking and comparatively thinking about what they're doing.
And all of these that you have here, those are all prime numbers. But if you would have had, if one of those would have been like a 14, for example, you can even break that into its factors and multiply in different orders. I feel like that was really revolutionary for me when I realized you could do that. And that's kind of what this is teaching too. These are all factors, and we can just, because of the commutative law, we can do them in any order.
Like,
Well,
let's say, go ahead.
In Singapore, when I look at the equation, I remember my teacher, I just can hear her in my head and say, look at the top, look at the bottom, what can you cancel? And how can you simplify? And so in this case, there's nothing that I could simplify, that therefore I go multiply across. But she always said that, and it's almost like a hack, but we never knew why. So thank you for showing us why.
That's been my goal this summer, is to really go step by step so that we can see why we're doing what we're doing and see the commonality of the processes and the patterns that much of what we've been taught in arithmetic hides. Because if we just have to learn keep, change, flip, right? We're not going to learn that today. But we learn these little things that teachers say, or the butterfly method for adding two fractions, or multiply across. We think that there's just all of these different ways of doing things instead of recognizing there's one way that everything can operate if we just think through it. And I think that will help our students to recognize the patterns and ultimately be much better mathematicians instead of just remembering all the different rules.
Jana has
go
a
ahead.
thing in the chat. She said, "Is canceling the wrong word? Can we use canceling?"
Well, you can use canceling.
You can't. Sorry, I was just saying. My point is, we call it canceling. That's the trick, but that's not really what we're doing. What we're really doing is multiplying by 1 and using the identity law. So that's what I was just saying. Like we say canceling, but that's not really the right verb if we're being accurate.
And isn't that to me is what the part of what the classical method is all about, is using the correct language.
Mm-hmm.
So imagine if, with just what Jana said, with our youngest students, when we're simplifying common factors, and we're going to talk about it in a minute, we've talked about it several times, but if every time we do that with our students, we go, oh, look, we have common factors. That's the identity law. Oh, look, we have common factors. That's the identity law. If we talk about that being the identity law every single time, they're going to understand what it is, even if they don't understand it right away. Eventually, because we're giving them that peg and that repetition, eventually it will click. And they're going to go, oh, because it's 1. And that's early on when we first joined CC. And people asked me, I used to say that a big part of being classicalists was using the proper language when we talk with our children. And I think, Lee, I heard you say that on a recording or something somewhere, instead of just going, oh, that's a pretty flower, being able to use the correct name for the flower or different adjectives to describe the flower if you happen to know what kind of flower it is or the color. But the more accurate language we can use, that's how we help our students to learn and grow themselves. Okay, so I have 2 examples here, side by side, of what it means to divide a fraction. So on the left, I'm saying that we can rewrite this as multiplication by the reciprocal. And there's 3 examples. I have 5 divided by 2. The reciprocal of 2 is 1/2. So I can rewrite that as 5 times 1/2, or 5 halves. Let's say I have 5 halves divided by 2. That's our second line. Oops, trying to turn my pointer on. And I want to divide that by 2. So again, my reciprocal of 2 is 1/2. So now I have 5 halves times the reciprocal, which is 1/2. 5 halves times 1/2. 5 times 1 is 5. 2 times 2 is 4. And that may make sense to us, because if I said I have 5 halves and I want to divide that in half, right? Our brains can maybe see where that becomes 5/4. But this is a way of understanding why that works using multiplication by the reciprocal. And then finally, we have 5 halves divided by 1/2. Now, when we're dividing, just as a way to think about this, remember, if I have 5 and I say divide that in 2, I can say I either want to find the number of groups of 2 things or the number of things in 2 groups. All right, so I can have the number of things would be in 2 groups, or the number of groups that have 2 each. So I would have 5 halves, or 2.5 things in each group if I had 2 groups. And when I have 5 halves and I divide it by 2, again, I'm saying how much would be in each group if I had 2 groups? 5/4 of a thing, right, of a unit. Or if I had 2 in each group, how many groups would I have? Well, I'd only have 5/4 or 1 1/4 groups. So when I look at 5/2 divided by 1/2, I'm saying, well, if I only had half a group, how many would be in each group? Or if I had 1/2 of a unit in each group, how many groups would I have? So in language, that's what I'm asking. And I think sometimes when we say that out loud, it will help our students, just like Jana was saying, I can start to conceptualize this thinking of scalars. We can also help our students to conceptualize if I have five halves and I wanted to put 1/2 in each group, how many groups would I need? And then we see, well, I would need 5 groups. But I can write this as multiplication by the reciprocal. So I have my 5/2 times 1/1/2, right? 1/1/2 is the reciprocal of 1/2, which is 2. Usually we skip this step here and we just go straight to 2 because we just flip them for the reciprocal. But technically this is the correct rule for reciprocals. So 5/2 times 2, I could either simplify or simplify at the end, but just following our process through, we have 10/2, which is 5. So that is rewriting our division as multiplication by the reciprocal. The other way that we could do this is to rewrite division as a fraction, and where we have complex fractions, simplifying those. So again, starting with 5 divided by 2, if I rewrite that as a fraction, I go straight to 5/2. Here I have 5 divided by 2 divided by 2. So my 5 divided by 2 is my numerator, and my 2 is my denominator overall. Notice that this winculum is a little bit longer. So it's hard to see on the screen, but it is longer. It may be hard to see in your booklets, but there's always one that's a little bit longer because the winculum is a grouping symbol. So this tells me, since this is the longer one, that this is the part I have to simplify first, right? I would simplify these parts first if I could. Now I can't simplify this any, so I leave it this way. And instead, I'm going to say, okay, I need to get rid of this 5 divided by 2. Well, 5 divided by 2 times 2, right, is where I would end up with my 5. So I'm going to multiply by 2. But if I multiply my numerator by 2, I need to multiply my denominator by 2. So 5/2 times 2 and 2 times 2. And that's where I end up with, in this case, these 2's are going to simplify to 1. So that's my identity law, leaving me with 5. Here I have 2 times 2, which is 4. So I get the same answer as with my multiplication by the reciprocal, but I'm now using complex fractions. And then finally, again, this side, we used the multiplication by the reciprocal. Here, I'm going to now have one fraction divided by the other fraction. I can't simplify them, so instead I'm going to multiply again by 2/2. And that will simplify to 5 in my numerator, simplifies to 1 in my denominator, leaving me with 5. Both of these are equivalent. They give us the same answer. Some of your students may prefer this. Some of your students may prefer this. In the math map, they're going to see complex fractions that they need to simplify. So practicing this is good. But this is also important, especially if we're dealing with some variables and things like that. Being able to rewrite it this way is also helpful. Any questions about division by fractions? it is probably the one that is hardest to intuit. And that's why I would go back to asking your student to think about, especially if you take objects, right? Say to them, okay, if I have each of these objects is a half, and I have 5 of them, right? We can call anything, right? So I can take my 5 objects and say I have 5 halves. Each of these represents a half. So put 2 in each group and then let them, right? I'm going to take 2 in each group. How many groups do you have? Well, I have 2 groups and 1 left over, which is half of a group. And that will let them see in a concrete, practical way what we're doing when we are dividing by a half, right? Because I'm putting, or how, if I had a half in each group, that's a way that you can actually help them to visualize what's happening as they separate things out. So we can take these expressions, say them out loud, talk about groups and numbers in groups, and play with objects in order to try and help them get enough experience that it starts to make sense to them without having to stop and think through all of the fraction notation. Right? If we give them those pegs to hang on, then we go, look, here's the notation that describes what you just did. I think that will help them to demystify what they're doing. Okay, so let's attend when we're dividing fractions. So remember, multiplication is associative and commutative. Division is not. So if I had 5 divided by 2 divided by 3, I cannot reassociate this and say 5 divided by 2 divided by 3. I cannot commute this and say 5 divided by 3 divided by 2. This, if I was to write this out, taking my first division, it would be 5 times the reciprocal of 2 divided by 3. So that's 1 over 2 divided by 3, which I could write as 2/3. And the reciprocal of that is 1 over 2/3, which is 3 halves. And I end up with 5 times 3 halves, or 15 halves. How many would have guessed that you were going to get 15 halves when you saw 5 divided by the group 2 divided by 3? Not me, because I would need to do several of these before that became intuitive. That's why I say division, I think, is probably one of the division, when we're thinking about division, and especially division with fractions, it's less intuitive than some of the other things that we do. And so writing out the steps and helping your students to see what happens is going to be helpful, and helping them to see that those grouping symbols matter. And so remember, the winculum is a grouping symbol. So here you can go, you see this is the longer bar. So, and here's my longer bar. So notice that my 5 divided by 3 divided by 2 is not the same as 5 divided by 3 divided by 2. Because I have to simplify differently in different places. Right. Any questions? All right. Now, where does it get ugly? It gets ugly with mixed numbers, right? Mixed numbers get really ugly when we are multiplying and dividing. And honestly, I don't even think that I did an example with dividing mixed numbers, because I would just use improper numbers, and we'll talk about that on the next slide. What we need to remember is when we have mixed numbers, there's a hidden addition here. So 3 1/4 is 3 plus 1/4. 2 1/3 is 2 plus 1/3. And so what do I have to do when I'm multiplying two-term expressions?
You have to distribute.
I have to distribute. So I have to have 3 times 2. I have 3 times a third. I have a quarter times 2, and I have a quarter times a third. Okay. So here's my distribution. Then I'm going to simplify. So 3 times 2 is 6. 3 times 1/3, multiplicative inverse, that's 1. And then I have 1/4 times 2. And so that simplifies to 1/2. And then 1/4 times 1/3 simplifies to 1/12. And now I have my fractions yachting. That's where you were asking, right? Halves and 12ths are not the same. So I can make my halves into 12s so that I can add, and I get 7 and 7/12. If this step and this step doesn't go well, you don't get to this step here. However, if we were to take and convert our numbers to improper fractions, the 3 1/4, and I'm showing you all the work, becomes 13 quarters, and 2 1/3 becomes 7/3. Now I can just multiply, and I would get 91/12. And if I wanted my answer back in a mixed number, then it's right, we talked about how to rewrite that as a mixed number. If I was going to divide, this is the only way I would divide, right? I would just divide my fractions. I would not try to divide here, because first, to find the reciprocal of 2 plus 1/3, I'd have to convert this all to thirds, then find the reciprocal, then multiply by 3 1/4. And then I'm still going to, at some point, have to find a common denominator again. So when it comes to mixed numbers, multiplying and dividing, I would always say that it's going to be the most straightforward case to convert to an improper fraction and then multiply and divide. And if needed, you can always convert back.
So whether we come to equation, how do we help our kids to and ourselves to find the path of least resistance? You know, like in this case, improper fractions are easier. And in other cases that, you know, if you were to convert them using associative law or group them together, it's the easiest. Sometimes using bar models are the easiest. Maybe we're not looking for the easiest route, but should we be advising them to think ahead or think a different way to find a path of least resistance?
I think, yes, I think as you offer your students, so with your youngest students, I would give them the way that is going to lead them to truth and not skip any steps, right? I would say, let's go ahead and we're going to do this correctly so that you see the steps and understand why we're doing what we're doing. As they become more familiar and they become quicker calculators, then I would say, is there another way we can do this? Consider this. As they become familiar with multiple ways, let them say, well, couldn't I just do this? Could I do this? Now, I prefer to almost always work with improper fractions when I'm calculating because it is almost always easier. And it makes sure that I don't accidentally think that 3 1/4 is the same as 3 times 1/4. So I tend to always prefer improper fractions. I think we do them a disservice in calling them improper because it gives people this sense that they're not the correct way of writing a fraction, but they really are. They're just written in an improper, right? So I think the name makes us hesitate, but for calculating, I really think that that's a better alternative most of the time. Now with younger students, if I'm adding 2.5 and 2.5, that's a case where I would say it's going to be more straightforward to let them see I'm adding my 2s, I'm adding my halves in that case. but especially with our students that are starting to do anything that's a little bit more challenging with numbers that are a little bit bigger. In this case, I would encourage them to use improper fractions. All right, so I called this attending to elegance. Could I simply multiply my numerator and then multiply my denominator and then look for common factors? Could I do that? Do I want to do that?
No.
No.
Unless you have a calculator.
Yeah, sometimes our students can sometimes, and we are changing the mold. So I'm saying this, and what I really should say is that traditionally educated students oftentimes see this and they don't stop to think, right? Which is what Yating was asking, how do we help them to think? They just jump in and they say 2 times 3 is 6 times 1 times 15 is 90 times 5 is 450. Oh, wait, can I use a calculator? And they just want to jump in and do the process that they've been taught how to do. But what is more elegant is to do what we have talked about doing, right? And that was canceling or simplifying by finding common factors that become the identity law. So do we have any common factors? Is there a common 3?
Yes, there's 5s and 3s, 11s and 2s.
All right, so hang on. So here we need to be careful because we need to make sure we write the other factors. We don't lose that. Mm-hmm. So here I have 2 divided by 2 is 1. Okay, any others?
You have an 8 on the top and then a 4 and a 2 on the bottom toward the other end.
So there's 8. 2 times 4 is 8. So I can simplify those. All right, anything else?
Fourteen over 7 is 2.
Okay, so there's a 2 and there's my 7.
And just so we can tell your children, as Kirsty's not crossing it out, she's writing as a 1. So 14 sevenths became 2 firsts. So that's what our notation means.
And there's a 15 in the numerator. You could turn that into 5s by multiplying 1/3. There's
3 on the right.
Oh, yep.
15 and 3s.
So that 3 and that 5 are 15. So 15 over 15 is 1.
Mm-hmm. You do that too.
There's so many ways.
3 in the denominator toward the end and a 21. So you could do that, make that a 7 in the numerator.
Yep.
Now your 10 over 5 cancel. Or your 10 over 2 times 5, I should say. Cancel to 1. Reduced to 1.
All right, anything else?
Or 8 and 9. Or 56 is 8 over 56 ninths is 8 over 1.
I think I should have made this
54.
54. Yeah, that's what you
We
meant.
just changed the problem.
Yeah. So there we go. So that leaves me with 6 and 9. Where's my 6? It went away. So now I don't have any factors left in my denominator. And so I have 7, 2, and 6. Is that terrible to multiply? No. What's that?
84.
84. So our students have a tendency to see things like that and go, oh, I can't do this. Or can I use a calculator before they even think? But notice that once we started looking for common factors, it would simplify to 1 and let us apply the identity law. We got to something that we were able to calculate fairly straightforwardly.
Nice.
So if we want to practice this, notice I have a really long list for pre-practice this week. So before you even start multiplying and dividing fractions, practice scaling units with concrete examples. So if my units are milks, right? So little milks, right? I have 2 little milks. So I could count my little milks and scale them. I could count by 2s or dozens of eggs, whatever it is that you're doing. This is where you say, okay, this parking lot has 5 cars, and this parking lot has 5 cars, and this parking lot has 5 cars. So if I have 3 parking lots that have 5 cars, how many cars do I have altogether? So now I'm scaling my 5 to get 15 cars. We can do that with these great with concrete examples. Sticks, rocks, whatever you want to do if you're outside, toys that your kids have. So scaling units with concrete examples. Then practice scaling fractional units. And one of the best ways to do that is just by folding. So take a piece of paper and mark your fourths, and then take a fourth and fold it in half. Right? Or a third. So just practice folding in halves and thirds and fourths to help them see that that unit gets smaller when I scale it by another fraction. Practice writing reciprocals. What's the reciprocal of 5? 1/5. What's the reciprocal of 1/5? 5. Do them in pairs so they see that it can go both ways. Practice rewriting division as multiplication. And then practice rewriting with your commutative and associative laws so that they can see how those pieces go together. Then, once I feel pretty confident that my students have these skills, then I would say create your random fractions, multiply them, and divide them. Right. But before you get there, these are the skills that I think you need to practice before you ask your students to multiply fractions and divide fractions. Now you can just tell them what they're doing and have them do that. We've talked about that before, that we can come at understanding both ways, one through step by step growing towards it, or by jumping in and letting them see what the algorithm is, but then connecting the algorithm to meaning later. Both are okay. But if you're looking for what's my pre-practice, these are the things that I would say to practice before you actually start multiplying and dividing fractions. Nicole.
This is really helpful. One thing I'm struggling with throughout the call is a working definition of the word scale. Because on one hand, I'm like, does it just mean multiply? But then when you use the folding paper thing, I think I got lost. So I can go back and rewatch this a few times, but if there's like a place that kind of spells out a working definition of the word scale, that would be helpful.
A scale is just to tell me how much of something I have. So if I was to take my piece of paper, I'm trying to find an easy piece of paper. This isn't going to work. Right. I have my piece of paper and I fold it in half. And then I fold it in half again, and I have fourths. So now I can say to my student, right, it's a sticky note, now it's stuck to itself, right? Each of these sections is a fourth, right? Scale that by 3. So how much would 3/4 be? Well, it would be this much of my paper. How much would 2/4 be if I scaled it by 2? It would be this much. How much would 4/4 be? It would be the whole paper because I'd need all 4. What would 5/4 be? I'd need another piece of paper, right? I'd need another fourth. So I'd need another piece of paper to show 4/4. What would half of a fourth be? Well, if I was to take my fourth and fold it into half, right? I can see now visually that this is half of a fourth, which of my original, right? If I fold my whole paper in half, of my original, this was a fourth, because there were 4 parts. But now if all of them are divided in half, there's 8 parts. And so half of a fourth is 1/8. So that's what I mean so scaling is telling us how much of the fourth do I want? I want half of it. And so I only want this half. And we can folding our halves and fourths and eighths is going to be the easiest, right? Folding thirds is a little bit trickier, but we can still do that. Or even if you start with, you give them the thirds and let them fold it in half. I think that this type of folding is just going to help them to see what happens when I say I want a small, right, half of a fourth. What if I said I want a fourth of a fourth? Well, I'd have to divide this I'd have to fold it twice in both directions, right? And I'd see that this little piece here becomes a fourth of a fourth. And if I was to look at my whole, there would be 16 squares this size. So 1/4 of a fourth is a 16th of the whole. So that's what we mean when we say scaling.
Okay,
And I
that's
just really,
good. And then of is like multiplying. Like that's how when you say the word of, you're talking about multiplying.
Yes, that's all we're doing is we're just using language to help us visualize what multiplying is. Because that's what, if we wrote it as if we wrote this as an operation, we would write multiplication, but we are using language to help us not get stuck on the multiplication idea, but to help us.
Yeah, because now I'm trying to figure out what would be a good way to explain that of is the same as multiplying. I got to think through that. I'm not expecting you to do that.
Well, and it is, right? So if you just anything that you say to your kids, we use of a lot. I have 5 of these shoes. I have 6 of the bananas you bought. Right? What do I mean? I have 6 times that, or I have 6 bunches of 3 bananas. How many bananas? And they'll go, well, that's 18. Yeah, because you're multiplying. So we use it in our natural language. And so we're just connecting that idea that this natural language use of is the same thing as multiplication.
That's very good, very helpful. Thank you.
You're welcome. All right, well, we are over time, so I'm going to leave us on this slide and invite you to join us next week where we start rationals and binomials, looking at ex nihilo, and I encourage you to go and jump on the Common Latin Book Club and have fun with Latin this week, and I look forward to seeing you all next week.